We're very privileged to have Professor Steffen with us, one of our leading Earth system scientists. Excited that he's come across to share what he's doing. So he's a councillor on the publicly funded Climate Council of Australia that delivers independent expert information about climate change. He's also an emeritus professor at the Australian National University in Canberra and a senior fellow at the Stockholm Resilience Centre in Sweden, where we see a lot of this work coming through. And a fellow at the Bezier Institute of Ecological Economics in Stockholm. So this has been his life work and what he's really passionate about. And we thought it was a great opportunity to bring somebody who's knowledgeable and been involved in this for a long time around the world to really help us frame this and think about what is it we need to be thinking about? What are the facts about the situation? And start to put some information and context into this debate that's running through our society. And one of the key things I'd ask you to consider, how do we take this further? How do we educate? How do we bring in people to understand and to start working with the questions versus the one-liners and the beat-up we see so often? So be interested in your thoughts as we go into the panel. So over to you.
Lovely introduction. And it's great to be over here again. There's been a lot of interest in this issue in New Zealand. It's my third trip across in about the last 6 weeks. And I've got 2 more coming up. So I'm getting more invitations from New Zealand than I am from Australia, which probably represents the politics in the 2 countries at the moment. Okay, so I'm going to talk about climate change, but in a broader context of a new concept called the Anthropocene, which the second half of my talk will be about. So climate change is a huge issue, but it's part of an even bigger issue that's looming up that we have to deal with. But let's dive in then and talk about the climate issue straight away. So I'm going to start on the other side of the Tasman and looking what's happened over the first half of 2019 in Australia. January was an unbelievable month for us, and I just saw this morning in my news feed that in the Northern Hemisphere, this has been the hottest June ever recorded. So it's happening all around the planet. This was the hottest January by far that Australia's seen since we've kept records. But at the same time, we've had massive rainfall. That's the regional city of Townsville in North Queensland, which got so much rain that the entire place flooded. You can see that. And it'll probably never fully recover because it was such a massive flooding event. That was also in January, by the way. And also in January, this is Tasmania. These are some of the forests that resemble those that you have on South Island in New Zealand. Tassie's the only place we have them. They're disappearing fast because they're drying out, extreme heat. They burn, and they're not adapted to fire, as you well know, and they get replaced by eucalypt forests, which are adapted to fire. All of this happened in 1 month earlier this year in Australia. The data behind it, I think, is even more remarkable. This is a map of Australia, color-coded, and you see this pink range there. That's 40 degrees Celsius. So during a 2-week period in January, at one point during that period, that part of the continent that's shaded pink and darker saw 40 or upwards in temperature. Over 80% of the continent, people were experiencing 40 degrees. We've never seen anything close to that in the over 100 years of European records of climate in Australia. To me, this is just as remarkable. This is the rainfall for Townsville area, and the way it's mapped is this is 1 January, and that's the end of December. So that's going through the year. The black line here is the long-term average. That's that line. So the rainfall comes in the wet, which of course is in the summertime, and then it steadies off and a little bit at the end. That's the average. This line is a 10-day period in January. They got 50% more than the entire annual average in about 10 days. That's why they had massive flooding. And that's totally off the charts, even of any type of variability we've seen. So clearly the climate system is really shifting very fast. So this is really what climate change looks like. We're putting together a report with the Climate Council that we're going to release in about a month's time. These are visual images, all from Australia, of what climate change looks like. Underwater, 50% of the Great Barrier Reef looks like that now. 50% has been killed of shallow water corals. And these used to be seagrass beds. There's some of the Tassie alpine area. That's the Murray-Darling Basin. All of these, climate change is the major factor why these systems are changing. We can see it in the animals as well. That's a massive fish kill. Hundreds of millions of fish in the Murray-Darling River were killed. Combination of taking off too much water for agriculture and heat. What water was left heated up and the fish died. These are our baby flying foxes from Queensland. We've kept them alive. They're being chilled down. Their parents dropped dead from heat out of the trees, and we saved some of the babies who are hopefully coping now. These are dead black cockatoos from Western Australia. Again, they fell out of the trees dead from excessive heat in the 40s. They couldn't even fly. You'll probably applaud the next one. These are possums, and dead possums. And what happened to these creatures is that they were suffering from both heat and drought. They crawled to get some water, and unfortunately they hit salt water instead of fresh, and they died from drinking salt water. So these are all incidents that have happened within the last decade within Australia, all directly related to climate change. So we're seeing the impacts now. It's something that we are living with day in and day out. So it's one point I want to make to audiences is that you can actually see climate change and what it does. And there's a koala on life support, again, suffering from heat stress. And when you saw that map I showed you of most of the continent over 40 degrees, our biota are not adapted to temperatures like that. We humans can get into air conditioning, they can't. So this is really what climate change is looking like across the Tasman. Well, what about New Zealand? You're probably more familiar with this than I am, but in the IPCC reports, when they look country by country, this is what's happened here. Obviously, you're getting more extreme heat events as well, but it's quite a different profile from the Australian profile. Some drought, but not nearly as bad as what we're hitting. But these last two are more unique to you. Extreme sea levels are rising, and of course, you're very much a coastal country, as are we. And there's coastal erosion and high sea level events occurring around parts of New Zealand. South Island, this is important. Loss of ice is occurring at an increasing rate. Ice volume has declined by somewhere between 35 to 60% from a century and a half ago up till now. Glacier volume reduced by 15% just from 1976. So in terms of cryospheric change, these are actually very fast rates of change. Fortunately, I just flew in yesterday through the front, so there is some snow falling now, so perhaps there'll be a bit of snow up in the Alps. There are a lot of consequences for business, no matter what business you're in. These are pretty much generic things. Even if you're in the ag business, you obviously have supply chains and disruption of supply chains. Good example in Australia was Townsville, where they were isolated for about 2 weeks, disrupted all sorts of supply chains throughout northern Queensland with economic flow-ons. A big one for us in Australia is that the social license for mining coal is disappearing fast. You saw the pictures of the student strikes, and that's actually starting to hit us. Perhaps in discussion I'll talk about some legal cases I've been involved with in stopping coal mines on climate change basis. Consumer investment action. I work a lot internationally in Europe with finance companies. They're thinking very carefully now where they're putting their money for two reasons. One is the ethical, but also they don't want to have stranded assets when the world starts to take action on climate change. Political instabilities, it played a role in our election earlier this year. And of course, the emergence of disruptive technologies is also very important. Think of the digital world. Okay, let's get on then to the science of climate change and just go through some of the basics. What this is showing here is a record of global average surface temperature. So it's measured at about 1.5 meters above the land and above the ocean and above the ice around the world. So we had enough measurements from 1880, we could get a global average. And so this shows that global average all the way up through 2017. And you can see that from about the mid-20th century, from about 1950, there's been an extremely strong warming trend. Overall, we're about a degree or 1.1 degrees above pre-industrial, which is actually back a little bit before this. So it's very clear that the climate is shifting very fast, mainly since the mid-20th century. So obviously from year to year you see variability, which is often misinterpreted as a pause or something in warming. But we usually take at least a 5-year running average, which is the red line, or more appropriately, about a 30-year average will give you what the long-term trend is really doing. If If you look at the shape of that curve and then look at the shape of this curve, you can see that the correlation is exceptionally strong. These are emissions globally from 1900. The gray are fossil fuels, almost entirely. The industry is cement industry, but that's less than 10%. This is land use change. And most of this comes from the tropics, from Amazon, Borneo, and so on. And it consists of deforestation for soya, for palm oil, for things like that. So these are carbon dioxide emissions. These are not methane emissions. So this is the main driver of climate change. It is the long-lived gas which really regulates climate in a long-term perspective. And you can see the correlation is exceptionally strong, and so is the physics. We've known the physics for about 200 years now, that it is a very potent greenhouse gas. So the latest report from the international science community was the special report on 1.5 degrees. That came out of the Paris meeting in 2015, where the world's countries, I think all but one country, and New Zealand, of course, and Australia, signed up to the fact that we would do everything we could to limit warming to well below 2 and aiming for 1.5. The interesting thing was that was pushed through primarily by the small island states, north and east of New Zealand were the primary ones. Tuvalu, Kiribati, countries like that, whose very existence depends on nothing more than 1.5. There's actually a big difference between 1.5 and 2. A half a degree doesn't sound like very much, but here are some differences between 1.5 and 2. So persons exposed to severe heat waves reasonably often, every few years, about 1 billion at 1.5, but nearly 3 times as many as 2. So a lot of these are highly nonlinear functions, where small increases in temperature make a big difference. Transformation of land ecosystems, that's what I was showing you with Tasmania, where fires or other disturbances come through. With the new climate, the ecosystem shifts. Again, that'll about double, going from 1.5 to 2. And for those of us in Australia, this is important. Coral reefs experiencing long-term degradation, i.e. bleaching. At 1.5, 70 to 90% will be gone. At 2, they will become extinct. So the Upper Paris target will eliminate coral reefs around the world. Bear in mind, at 1 degree, the Great Barrier Reef, 50% of the shallow water corals are dead and will not come back. So these are important differences. And to give you an overall context of what these temperatures mean, I often ask people, particularly students, we know that the Earth has been in ice ages and then warm periods. And the last ice age began to end about 21 to 20,000 years ago, when the Earth warmed up to the present about 11,700 years of fairly even, warmer, wetter climate. I asked them, what was the difference between an ice age and a warm period? And most of the answers I get is 20 or 25 degrees. The answer is 4. So if you would cool a climate by 4 degrees in terms of global average temperature, you'd go into an ice age. So these global average temperatures are really, really important. They're not what you feel. It's not like going from 22 to 24 degrees. It's a change of state of the Earth's system as a whole. So 2 degrees is already halfway upwards to the same level of warming as between an ice age and a warm period, but in the opposite direction. So these are actually very significant, as you can see from the numbers. All right, here's where the notion of a climate crisis comes in. So we're already seeing it. We're seeing the impacts. And we know they're going to get worse even with a half a degree or another degree of warming. So here's the issue. How do we stop this? Well, we know, using a so-called carbon budget, how much more carbon we can emit for a given temperature target. So obviously the budget for 1.5 is more stringent than the budget for 2, which is more stringent than the budget for 2.5. But you guys work with budgets all the time, so you know what budgets are. When you want to target a business target, employment target, or something like that, you put a target and then you try to budget to meet that. We do the same thing with the climate system, but our currency is carbon. How much more carbon we can emit for a given temperature. So here's some graphs that show what our budget looks like for a 2-degree temperature rise, and then the emission reductions we have to do to meet that. So the gray line are the observed emissions up to about 2015 or 2016. And that's observation. So we are emitting, this is in billions of tons of carbon dioxide. So the the weight of the oxygen atoms included here. So we've been going from the upper 20s from 1990, and we just breached 40 billion tons per annum a couple of years ago. But if we want to limit warming to 2 degrees, this is the curves we have to follow. And the broken line is if we have a little bit more generous budget. So you can put a budget in, 600 billion ton carbon budget is for a 2/3 chance, 2/3 probability of meeting a 2-degree target. If we relax that to only a toss of the coin, 50-50, we can burn more carbon, which is that broken line. But the point I want to make here is that delaying just a few years makes a huge difference to the shape of that curve. All three of those curves have the same area underneath them. That's the budget. And so if we stick to the budget, if we could have peaked emissions by 2016, we have out to 2045 to decarbonize. Our next hope is 2020, next year. That's the yellow line. That means we have to decarbonize by 2040, in 2 decades. That's pretty fast. But notice if we just delay 5 years, it's impossible. You cannot meet a 2-degree target. That's the climate crisis. And it's a hard one to get your head around because most crises are immediate. An enemy's at your doorstep, or a massive disruption has occurred to the economy or something. This is a slow crisis, a bit like slow violence. But you have to understand that delaying here makes things impossible. So it is a crisis. The students are right. The New Zealand government is right. You have to actually put in place a plan now. Doesn't mean you have to get emissions down now, but you have to have the plan in place so that you have a couple of decades to do it. Waiting 5 years is going to make it impossible. So this is really what the crisis is all about. So how do we do that? Well, the first thing we do, and this again is where you guys are really unusual because you've basically already done it, is to get carbon out of the electricity system. That's the low-hanging fruit because we can do that. And of course, that's what we're attempting to do in Australia, running into a lot of vested interest, political fight back. But we have enormous renewable resources. My city of Canberra is now 100% renewable. We did it in 9 years, and we did it under budget. So you can do it. So, pathways to limit warming to 1.5. The point is, it's possible, but this is a statement from pretty conservative report. Rapid and far-reaching transitions in every aspect of life. And these transitions are unprecedented in terms of scale. In other words, humanity hasn't done this before. We've done it just as fast, and that was in the lead up to World War II, when the Western democracies mobilized in a period of about 5 years. And that was an enormous transition, very fast. But it wasn't of the size we need to do here. So it's going to be a big challenge. Okay, that's the CO2 challenge. A little bit now about what's important for you is methane and nitrous oxide. So we'll talk a bit about methane. This is an interesting graph. It's complicated. There's a 0 vertical line. All those bars on the right are human forcing of the climate. And their length is the importance. That's CO2, that brown one up there. So that's the most important one. The next one is methane here. It's actually a number of gases, short-lived gases, but that tan one is methane. It's very important, second most important compared to CO2. But it has a very different characteristic. It has a very short lifetime in the atmosphere. About half the methane's gone in 12 years after it's emitted. It's oxidized to CO2. But it's very potent. Depending on how you average the warming potential, it's 20 or 30 times more potent per molecule than CO2. So it's got very different characteristics, but it is an extremely important gas. This is the methane, oops, we went too far. This is the methane curve. This is how methane has been changing. This is a globally averaged number. So we thought, looking at this, that things were stabilizing out and that we were starting to get methane under control. But unfortunately, from about 2008 or 9, it's crawling up and the rate has increased yet again more recently. So there indeed is a methane issue that we have to deal with. Source is not well understood. Interestingly, we can pretty much rule out agriculture. So agriculture is probably not the culprit of this rise. It's possibly wetland emissions, And that's actually a natural feedback because wetlands are warming. And as wetlands warm, they're going to emit more methane. So that's a natural feedback in the system. But the other one, and I think this is the big one, is oil and gas, particularly unconventional gas production, methane fugitive emissions. And that's probably the biggest problem that we face now. Particularly now, it's something you don't think about, but as people move out of coal, they're going into gas, and they are producing more unconventional gas. Here's the problem. Methane levels were considered stable in the pathway models prepared for the Paris Climate Agreement. So they didn't take this increase into account, which puts more heat on us in two ways. One is to get methane down, but two is to get CO2 down to compensate for that. So that's making it a little bit tougher. What about New Zealand? Some data I've got from Stats New Zealand, but also from the IPCC report on New Zealand's methane emissions. Sources globally, about a little over a quarter of all human methane emissions come from ruminants, from cattle. A fair bit also comes from wet rice production, and that's mainly an Asian issue as well. Greenhouse gas emissions, CO2 equivalent in New Zealand, that's everything, methane, nitrous oxide, CO2, increased by nearly 20% from 2000 to 2016. So that's a pretty big increase. The good news is methane emissions from livestock digestion increased only 4%. So what that's telling you is it's still an issue, but there have been some gains in the agricultural sector in terms of slowing the increase of methane emissions. So that's good news. The point is, though, we can't just cap it. We've got to start getting it down. That's the challenge. But agriculture comprised about 35% of gross New Zealand emissions in 2016. Again, a completely different emissions profile from Australia. So it is a big challenge. The good news is people are becoming aware of it, and things are happening. So the overall emissions increased by 20%, but methane from cattle only 4%. So that's somewhat a good news story. This is important globally, and it's important because of these things called short-lived climate pollutants. We scientists love acronyms, of course. We're as bad as the politicians on that, probably. And short-lived climate pollutants are things like methane that aren't in the atmosphere for very long, but they're potent when they're there. And they have some interesting possibilities because of that. So warming is currently about 1 degree, but we believe about another ½ a degree is stored already in the ocean, because the ocean and atmosphere aren't in equilibrium. 93% of the heat from climate change, greenhouse gases, is in the ocean. Huge. 1% in the atmosphere. So it doesn't take much change in the ocean to flip the atmosphere temperature. So we think it's going to rise, even if we get emissions to 0, to 1.5 anyway. In 15 years, we're likely to reach this in a worst-case scenario. But about 40% of the emission is due to these short-lived climate pollutants, and methane is the most important of them. What this tells you is there's an opportunity that if we can work out how to get methane emissions down over the next couple of decades, we can reduce the amount of increased temperature we're going to see. So it's actually an opportunity. So if we get rapid and deep reductions in these, we could hold warming at 2050 to 1.5 rather than the current trajectory of 2.1. And that's because they're both potent and short-lived. So it's both a problem but an opportunity to actually make a quicker positive impact on the climate than reducing CO2 emissions, which are hugely long-lived. So again, this story of methane is sort of a funny one. There's some real positive opportunities, and of course there are real problems because it's more difficult to get them out of agriculture than it is CO2 out of electricity, for example. So that's the climate story in terms of looking at climate change per se. That's just a quick overview of the methane story. But what I want to talk about now is going back to the original title of my presentation, which is the Anthropocene, and putting climate change itself in a much broader context of the planet, a long history of the planet, and the long history of humans on the planet. So we start with this idea that the Earth is actually a single system. So notice that there's no S there. It's the Earth system. So just like the human body is a system and it's made up of subsystems, you have a respiratory system, you have a nervous system, you have a digestive system, but you as an individual, as an organism, have properties that are characteristic of the whole human body, i.e. a body temperature. And if that varies too much, your doctor is not too happy about it. The Earth is exactly the same. We have circulation systems, all sorts of systems, but they all interact to form a well-defined, well-regulated single system. How do we know that? These are some ice core data from down south. This is from East Antarctic, and in fact, it's from the Australian Antarctic Territory. And so scientists can drill cores down into the ice, several kilometers down, and they can analyze layer by layer what's in those cores. And we can go back really about 500,000 years. This is 400,000 years. And we can look at CO2, we can actually look at methane, we can look at temperature, and we can look at dust, things like that. This is temperature from 400,000 years ago to the present. And look, it looks like a human heartbeat, very regular. It also looks like your blood pressure. Notice that your blood pressure is capped. And if your blood pressure gets too high, your doctor's going to be really concerned. Temperature is capped. Every ice age stops at the same level. Every warm period stops at pretty much the same level. This last one we're in now is a little bit unusual. It's slightly cooler, but it's much longer than the other warm periods. And that's allowed us to develop agriculture. Agriculture developed about 10,000 years ago, simultaneously in many places around the world. So this is the world we live in. We evolved about then. This is the planet that we are adapted to, our bodies have evolved into, and so on. So notice that we have lived through 2 ice ages, warm periods. But we have not lived through anything greater than 1 degree higher than pre-industrial. So right now today, we are living at the highest temperature that Homo sapiens has ever experienced. And we're guaranteed to go higher. So we're going to be in terra incognita physiologically into areas that humans have not evolved into. That's the last 100,000 years in more detail. There's the depth of the last ice age. There's the Earth coming out of it. And there's this 12,000 year period of relative stability where we've developed agriculture, villages, cities, and so on. So this is sort of a sweet spot for humanity. But this is the stability domain, which should be around for another 10 or 20,000 years, naturally, that we are now disrupting through climate change. So now let's put climate change in that long-term pattern of variability. This is a 2,000-year temperature record. So 0 is Roman Empire. To the best of our knowledge, there were no humans on New Zealand, back down through here. Humans came probably somewhere in here with the Maori, and then Europeans came later. I'll talk a little bit later about Australia, but Australia goes back 65,000 years. We have the only continuous human culture that's gone through the Ice Age and the transition to a warm period. So we're quite unique there. But the point is that climate's very stable during that period. So these are in tenths of a degree. There's been about a 0.1 to 0.2 tenths of a degree cooling during that time, hardly perceptible, but a very tight bound of natural variability. And that's due to things like ENSO, it's due to the odd volcanic eruption, it's due to some subtle changes in Earth's orbit, it's due to sunspots. But we know all this. But this is the last 100 years or so of human greenhouse gas emissions. You see that spike is enormous compared to the climate we've had over the past 2,000 years. And we can do some analyses of the rates. The background rate in temperatures, it's rising about 170 times faster than the background rate. In fact, we can go back 7,000 years and look at it. And that's why these animals are dropping dead out of the sky and out of the trees in Australia and struggling elsewhere in the world, because the natural world cannot cope with rates that fast. It's beyond their adaptive capacity, and they can't evolve fast enough. Atmospheric CO2 is increasing about 100 times faster than the background rate. In fact, during the transition from the last ice age, there was a big increase in CO2 of about 100 parts per million, mainly from the ocean. Because the ocean warms, it bubbles out CO2. But now our emissions from fossil fuels are about 100 times faster. The biosphere is the other major part of the Earth system. So think of the Earth system in its most fundamental form as 2 big interacting spheres. The non-living part, the geosphere, which every planet has, Mars has it, Jupiter has, but we're the only one we know of that has a biosphere, that has life. And these 2 are intertwined, and they interact all the time to form the Earth system. But we've been actually transforming the biosphere more than we have the atmosphere, which is a lot of people forget. A big report came out about 3 months ago, an assessment of what's happening to the biosphere called Nature's Dangerous Decline. So what we can see here is that nature is declining, and that's just a general term for species loss, for loss of ecosystems and so on, at rates unprecedented in human history. So we're changing the Earth faster now than at any other time in human history. Rate of species extinctions is accelerating. Estimates are within 2 or 3 lifetimes we'll have the 6th great extinction event in Earth history if we keep at the same rate. So definite trends occurring in the biosphere. You can see more detail here. About 1 million animal and plant species are now threatened with extinction, many within decades. And for us, this is important because we're eroding the foundation of our economies, livelihoods, and so on. I don't have to tell people who make a living off the land that having a healthy biosphere is absolutely essential for supporting humans in the long term. So the view of the biosphere isn't much better. In fact, it's probably worse than the view of the climate system. So a group of us that I've been working with up in Europe have tried to synthesize all this information. And so we did this first in 2004, and then we published updates of these figures in 2015. We asked ourselves a really, really simple question. If you had only 12 indicators that could describe who we are as humans and what we do, what would they be? So here they are: population, economy, energy use, foreign investment, and here are resource use and transport and telecommunications. Every one of these graphs starts at 1750, before the Industrial Revolution, and it goes out to 2010, the last year we had data. You can see the pattern. It's remarkable. It's an explosion of humans and our activity. But it's not nice, smooth lines. Again, this year, 1950, pops out. That's where the broken line is there. We exploded after the Second World War. Just a massive increase in humans and our activities. There's been a lot of good things come out of that. A lot of people have come out of poverty. We're living a lot better lives than we did 2 or 3 centuries ago. We're wealthier, longer lifespans, and so on. So we said that's really a remarkable set of graphs that describe human progress. But then we asked ourselves, as Earth system scientists, can we see any effect of this on the Earth as a whole? So we did the same thing for the Earth system. Again, from 1750, 12 indicators. The top 6 are the geosphere, the non-living part. So the greenhouse gases, there's the only one on climate directly, that's temperature. These are the biosphere. So you can see the ocean, the coast, and the land. And again, you see curves sweeping up. Not quite so neatly at 1950, although there is quite a bit of correspondence to 1950. So we made 2 major conclusions from these 2 graphs. One is that these graphs are correlated to the first set. In other words, there's a massive amount of scientific evidence to say this is not natural variability. This is being driven by human activities primarily. The second thing we can say is all 12 of these are outside of that 12,000-year period of stability that the geologists call the Holocene. So these 2 graphs are the fundamental evidence to say that geologically the Earth has left the Holocene. It began to leave the Holocene in 1950. And in fact, the geologists now have a working group that's been working for 10 years, and they just voted about a month ago, 29-4, that we Earth system scientists are correct, that the Earth has left the Holocene, and it's in the Anthropocene. Anthropo meaning us humans driving a new geological epoch in Earth history. So this is really what the Anthropocene is all about. The word comes from this gentleman, Paul Crutzen, who's a Dutch atmospheric chemist. He won a Nobel Prize, but not for the Anthropocene. He won a Nobel Prize because he was one of the scientists that worked out what was going on with the ozone hole, the chemistry behind the ozone hole and the CFCs. But when he saw this data, we first showed this data in the year 2000. We published it in 2004. He just said, well, we're clearly out of the Holocene. We're in the, and then he made the term up at the time. He just stumbled around for a word, and he said, we're in the, you can see his mind going around like this. And he just blurted out Anthropocene, and it stuck. Now you see it in the humanities, you see it in arts productions, you see it in cinema, and so on. And it comes really from the year 2000, from this guy, Paul Crutzen. So to look at our contemporary climate change that we saw before, We now do this in an Anthropocene perspective. And to do this, we need longer time frames. You may have seen these. These are the climate models that the IPCC publish. So we have temperature going up to about 2010 or so in this case. And then we have 4 model scenarios depending on how much we emit out to 2100. But the point here is that the amount of warming, which is this, here you see this 4 degrees is the same as an ice age, difference to an ice age. That's the high emission one. But the temperature rise is assumed to be in the models directly proportional to human emissions. Well, it makes sense. But remember, the Earth is a system with feedbacks in it. So some of us now are doing some research on this topic to say that, by the way, these are the climate projections on a 2,000-year time scale. So you see what an enormous shock to the Earth system that actually is. So it took about 7,000 years for the Earth to come out of an ice age into a warm period. That's 4 degrees. We could do the same thing in 150. It's an enormous change in the Earth system. So we're pretty much committed to 1.5 to 2. That's the Paris range. So we're sitting at about 1.1 today. We'll probably go at least to 1.5. So that's where we are today. There's the worst case, somewhere between 4 and 5 degrees by 2100. This line up here corresponds to 2100. So that's where we could go. And that's going to be tough even for modern societies to deal with. And a lot of scientists are saying that there will be some collapse and drop in population if we go that far. But the problem is, we think there are probably internal tipping points in the Earth system, that once we breach them, this intermediate range is no longer accessible. In other words, it will flip like a kayak turning over. It won't stay part way over. It'll flip, and the Earth will go to a hotter state. So in the last 5 to 10 years, there's been an enormous amount of research now, which really hasn't filtered through to the assessments yet on what these tipping points might look like. So we can see them, and we know them pretty well. They come in 3 types: melting of ice, particularly at the poles; circulation change like ENSO, very important for New Zealand and Australia; and the loss of these very big natural ecosystems, Amazon and the great northern forests and so on. So you can see they're all color-coded there. We know a lot about them, and we start to see change. So 2 big droughts in the Amazon in 2005, 2010. They're related to climate change. Fires went through part of the Amazon, and they lost about 10 years' worth of carbon storage. Comes back up to the atmosphere. So that's what a feedback is. It's naturally putting more carbon back in, additional to what humans are putting directly in. We think about 50 to 250 billion tons of carbon could be lost from permafrost, that's frozen soil, up in Siberia by 2100. So by comparison, our emissions are about 10 billion tons a year. That's 5 to 25 years worth of human emissions of carbon. Right now, emissions from there are low, but they're increasing. There is melting and there is bubbling of both CO2 and methane out of the permafrost. They may be contributing to that rise in methane, by the way, as well. Arctic sea ice, we've probably crossed a tipping point, and we'll be committed to losing it. This is an annual curve, decade by decade, actually, through the years. Less and less ice during the summertime. And that has its internal feedback, because as you shrink the ice, during the northern hemisphere summer, it absorbs more sunlight, warms regionally even more, ice shrinks even further, more warming, and so you get this feedback loop. So we think that's actually crossed the tipping point, and within 2 decades that'll be ice-free. You can take your kayak to the North Pole, and it'll probably be nice and pleasant and warm up there by then. Coral reefs, I mentioned that. We think we may have crossed a tipping point there, that they're not going to come back, because we know there's another ½ degree locked in, and that'll be enough probably to tip them to extinction. This is a big worry. Accelerating ice loss from Greenland. It is really increasing now at a fast rate. There's about 7 meters worth of sea level rise embodied in the Greenland ice sheet. That's how much ice there is. That's not going to happen overnight. Maximum rate with all ice melting may be about 2 meters a century, but 2 meters is a pretty big hit in terms of sea level rise. West Antarctica is starting to move too. We're losing ice there. So sea level rise is definitely, the rate of it is increasing, has increased over the last couple of decades. The other point we're making is that these things, these tipping elements, are not independent. They're linked, just like a row of dominoes. When you start pushing the dominoes over, they tip another one, and another one. So here are some of the interactions we actually can see. A really critical one is this one, El Nino thermohaline circulation. Thermohaline is the ocean circulation, El Nino. They connect the Amazon and they connect the poles. So the North Atlantic corridor is really important, as you can see, for these tipping cascades. And we see changes there too. So the concern is, where do you start knocking the dominoes over? Our best estimate, the best estimate when I get asked, is probably not below 1.5, but almost certainly by 3. So it's somewhere in between 1.5 and 3 we'll start knocking those dominoes over, which means the climate system is out of our control. It's going to shift to another state, whether we like it or not. So we did a little cartoon to show what this looks like. This is what we call a stability landscape. Think of it as a ball rolling around between high little valleys, deep valleys, ridges, and so on. So time comes forward. The Earth has gone through these nice cycles of ice ages and warm periods, just rolls between those two. That's what that graph shows. So it's down in an ice age. Every so often, Earth's orbit around the sun shoves it up here for a while, and then it rolls back down. It just does that very regularly. Now we're over here. We're on some sort of very vague landscape. That's that spike. We're outside of the glacial, interglacial cycle. We will not go into the next ice age. We've already eliminated that. But we don't know where we're going, because this is new territory. It's a landscape that's out there. We can go back 5 or 10 million years and see Earth was sort of rolling around, something like that, but that was a long time ago. But now we're the ones who are driving this. So we're hypothesizing here that there's a fork in the road here. These are the Paris targets. These are the targets to get biodiversity loss down. We call it stabilized Earth. So this is a human-managed valley that doesn't exist in real Earth system space, but we've got to make it, and we park it there and keep it there. It could be 1.5 to 2 degrees higher than today, but what we want to avoid is this tipping cascade, because this will take us over a cliff, a planetary threshold, into what we call hothouse Earth. What does hothouse Earth look like? You actually see hothouse Earth about 17 million years ago. It's called the mid-Miocene, and it was about 5 degrees hotter than today. There was very little ice. There was some ice still left on Antarctic, but all the northern hemisphere ice was gone. 40 or 50 meters of sea level rise compared to today. So we know the Earth can actually sit. That's a stable valley, and it'll be there for millions of years, probably. So this is our task now. So climate change looks really different now when we say our task now is to steer the Earth here and avoid that threshold. That's why the Paris targets are really doubly important. Can we actually make it live in hothouse Earth? Probably not. There's actually a map coming out. I'm not going to show it because I'm not sure I believe it well enough, but it shows a huge band of uninhabitable Earth. I mean, it's massive. New Zealand's still inhabitable, but most of us, virtually all of Australia is not. All of the tropics are not. So people will have to go to the poles. So I think more work needs to be done, but a lot of areas will become uninhabitable at 5-degree temperature rise. Rainfall patterns will make large agricultural zones, many of them unproductive. Classic ones, Mediterranean, northeast China. They're already drying out, so we know that. As I said, sea level rise could be up to 40 meters, ultimately likely. And some brave scientists have said the maximum carrying capacity of humans could be around 1 billion compared to 7.6, because we'll all be squeezed to the poles. So it's not sort of an Earth that you want to bequeath to your children and grandchildren. So people have really worked in this game for a long time are making some powerful statements. Christiana Figueres, who was the executive secretary to the big UN Framework Convention for many years, she says timing is everything. This gets back to the crisis idea, that we actually have to act now. The cost of climate change, these are her words, decades of development wiped out, redevelopment not possible, which of course is a recipe for collapse. What is required? And again, this is a direct translation from her earlier this year. Transformation the likes of which we've never seen or done. So it's a challenge. So the bottom line, magnitude, worst case scenario, could probably collapse the civilization we know today. I don't think it will make humans extinct. Some people have postulated that. I think we're cleverer than that, but I think it's going to be a really rough world. We have 2 years left to get our act together. That means we have 2 years to decide we're going to do it and start making plans. That's why bills like zero carbon are important now. Every year you act earlier gives you more time. Every year you delay makes it harder. So that gives you a couple of decades, out to 25 years in my view, to get this under control. We can still do that, but that window's closing. And that's why we really have to make the decision that we're going to act very soon. I'm going to close now because I've talked about the climate system and the biosphere, the geosphere and the biosphere. But now in the Anthropocene, there's a third sphere of the Earth system, and that's us. We call it the Anthroposphere sometimes. So I'm talking, what about humans and our systems? Because if we have to transform, we have to come to grips with the systems we've built and how we're going to change them. Very controversial topic. I'll put some pretty confronting stuff up here. This is one of the most confronting. This goes from 1960 when we first had CO2 measurements in the atmosphere, direct, from Mauna Loa in Hawaii. So that's the concentration in parts per million. That's the curve. Here's where we are in 2019. Notice here are all the policy meetings we've had. Kyoto, Copenhagen, Paris. Here's us scientists. We've been producing massive reports for 25 years. What's the impact of all that? Zero. There's been no bend in that curve. In fact, these bars are the rate of increase of CO2. The rate itself is going up. So we have a serious problem. That so far, the system we've generated in terms of conferences, science reports, and so on, has generated nothing in the way of effective action, which is why the students are getting up in arms, quite rightly. We've failed them. So our challenge is, we don't want to go there. You can see what these lines are. We've got that, start doing those deep cuts that I showed earlier. What's it require? Well, the students are telling us. That's Greta, the famous Swedish student. Remember, it was less than a year ago that she first sat outside the Swedish parliament. So it's amazing, less than a year, how they've activated. Here's her take on it. Says we've got big inequality issues in our societies, and that's skewing the whole economic system as well. And this is really powerful. You are stealing children's futures in front of their very eyes. I happened to be in Stockholm this year on the 15th of March with the big student strike there. They had about 20,000 people on the streets. I would say about 3/4 of them were either girls, young women, mothers, and grandmothers. Very dignified, very powerful. These are some of the things they said. When adults insist on behaving like children, children have no choice but to assume the role of adults. And you're running out of excuses, and we're running out of time. There's that time thing coming again. This is the Aussie version. You can see we still have a sense of humor, particularly after the last election, and that lovely Swedish connection as well to Greta. But this one's actually important, system change. So they're saying, look, we understand this isn't a quick fix. We have to change systems. So how do we change systems? This is an interesting book called The Systems View of Life. It's one of the best books I've read. It starts from the first single-cell organism on planet Earth. Why is this planet so unique? Nobody can explain it. These guys have a pretty good hypothesis. And I was originally trained as a chemist, so I love their use of chemistry to understand how first molecules that formed in primordial sea atmosphere on Earth 3.5, 4 billion years ago could actually form into life forms. Absolutely fascinating. But it goes all the way up to Homo sapiens, which is just this grand vision of what life is. But they make a powerful statement at the end. Our world today is dominated by a global economic system with disastrous social and environmental impacts. They call it predatory capitalism. And we're the only species, and this is true, we're the only species that actually undermine our own life support system, whilst knowing that we're doing it. So that obviously the signals in the economic system are wrong. But there's been some really innovative work on economics. This is another colleague of mine named Kate Rayworth from Oxford. And she's written a brilliant book called Doughnut Economics, the Doughnut. And she says, look, if you just sit back and say, what do you want an economic system to do? You want it to do a couple of things. One is There are a lot of human issues that we still think are really important, and they are important. She calls it the social foundation. There are equity issues. There's obviously jobs, income, education, resilience, energy. We need all that stuff. Health, importantly. So we have to provide that. And we have provided it really well through the Great Acceleration. But what we forgot is that there's also a ceiling, which, by the way, our indigenous forebears actually understood, is that you actually have to maintain your life support system as well. So she has this ceiling, environmental ceiling, and these are the 9 so-called planetary boundaries. This is a framework that scientists have developed to say, if you want a stable Holocene-like Earth, how far can you push it and where you should stop? And so this is a floor and a ceiling of what she calls a safe and just operating space for humanity. And she's written a book about this with some real nuts and bolts about how you would change an economic system to do that. It challenges the powers that be, but it's possible. So she has 7 points she makes. I only have 3 here. Systems thinking, dynamic complexity. We have a linear economy: resource, process, consume, waste. I think Tony mentioned that at the beginning. We have to start thinking about waste becoming resource streams. Close that loop. It's exactly what this is talking about, systems thinking. The economic system must distribute equity by its design. Not leave it to governments to redistribute income. The economic system must do this by the way it's designed. And of course, it must be regenerative by design in terms of the biosphere. And underneath this all is a new philosophy. This is an Indian philosopher based in the US. He says, our society is based on a human-centric. It's all about us. Just look at advertising. It's all about you as an individual, not even a society these days. But the Anthropocene demands a life-centric approach. It's all about life, not about us directly, but life. I'm giving the last word to my indigenous colleagues across the Tasman. As I said before, this is the oldest continuous human culture on the planet. It's the only one to go through the Ice Age warm period transition pretty much intact. It's survived on the roughest continent on the planet for humans to live on, and they understood exactly what they need to do. You can read that. But they understood systems, that we are part of a cycle of things, and we're only a tool in that. Our job is to keep the balance of nature. It's a big cycle of living with the land and eventually going back to it. So this is what the Anthropocene is all about, and I hope that in these 45 minutes or so I've convinced you that climate change is a crisis, but it's actually part of a bigger issue that we have to deal with, which is the Anthropocene. The bright side is we are a clever species. We can move fast. There are social tipping points. There are technological tipping points. The thing is, we've got to make that first step to decide we're going to do it, like we've done in crises before, and we still have 2.5 decades to do it, but we have to start now. That's the crisis. Thanks very much for your attention, and hopefully now we have some discussion. All the tricky questions are going to go to my panelists, by the way. So.